Assalamualaikum warahmatullahi wabarakatuh, and a very good day to Dr. Azizan. So this is our group. We will representative hydroelectric. So before that, let me introduce myself. My name is Muhammad Ikhwan bin Ibrahim. What my metric number is 198389 with my other three friends, Alif Akmal bin Omar, Muhammad Irfan Faiz bin Muhammad Jasni, and Ahmad Hushairi bin Alias. So moving on to the next slide. So the first thing is the introduction. So we do know that hydroelectric power is one famous invention. So from history, the first power plant was located in North America and the UK. Noted that China has been the greatest market in the terms of hydropower capacity. So the working regulation of the hydroelectric itself is quite simple. So firstly, water will be released from the reservoir and it will be then flow through a turbine, causing it to spin. So this action will activate a generator to produce electricity. So this process can be visualized as in a figure in the slideshow. If you can see on your screen at the left side. So the innovation of hydroelectric technology has expanded and created various shapes of turbine itself. So for example, we do have Pelton or cross-flow kind of turbine design. So the turbine design must be chosen according to the surrounding of the place that the blade will be placed and the output itself. So noted that hydroelectric is not only made up of one type of turbine design, but in various forms. So in this study, we will look through three types, which is the Pelton, franchise, and the common shapes of water turbine itself. Moving on to the problem statement.
Okay, thank you, Ikwan, for the introduction. So I will proceed on the problem statement. So nowadays, hydroelectric application gives a lot of benefit to society as it is known to be a clean fuel source. One of the things that make a hydropower system different from one place to another is the turbine shape. So basically, this study will evaluate overall performance of three types of turbine design under the same parametric study. The hypothesis will evaluate the effect of different turbines under the same angle of attack. So at the end of the study, the best turbine design will be chosen considering a drag force and the down forces. So that is what problem statement is all about. So I will proceed to the modeling stage. So for the modeling stage, we choose the SolidWorks software for our modeling stage. So the SolidWorks software was used in the model development of all three different types of hydroelectric turbines. The dimension size of the design is the actual part scale design. The major difference was the entire design of the turbine. So as mentioned from Ikwan just now, we have three different types of turbine. The first one, I will talk about the Pelton turbine. So as we all know, all turbines have blades, right? So the blades for the Pelton turbine are made of a circular disc on the periphery, of which several buckets evenly spaced are fixed. The bucket is double hemispherical bowl. A splitter acts as a dividing wall which divides the bucket into two symmetrical buckets. Okay, so talking about the dimensions of the Pelton turbine, the diameter of the body is around 13 cm. So the thickness of the body will be 3.05 cm. So the diameter of the bucket 4 cm. Each blade has two buckets, and the number of blades have 12 blades. So overall, I think we have about 24 buckets, right? So moving on to the second types of turbines, which what we call it as Francis turbine. So for Francis turbine, the runner can be split into two parts, which are the lower half and the upper part. The lower part is constructed of a small bucket. It uses the impulse from water to rotate the turbine. For the upper part of the Francis turbine, it uses the reaction force of water flowing through it. So basically, both parts will make the runner rotate. Okay, as we mentioned before, for the Pelton turbine, for Francis turbine, the dimension of the Francis turbine, as you can see in the slide, the diameter of the body for lower body is 17 cm. The diameter of the body for upper body, 13 cm. thickness of the body will be 0.5 cm, and width of the blade from the lower body is around 4 cm. So for the last turbine that has mentioned at the beginning of the presentation, we have the common turbine. So common turbine is basically this turbine design is created by our own. We choose a simple design as in figure below. The measurements of the turbine is standard, following the existing design like Francis and Pelton turbines that we have discussed before. So talking about the dimension of the common turbine, as we can see in the slide, for the diameter of the body will be 13 cm. The thickness of the body will be 5.76 cm. Length of the blade 14 cm. Width of the blade 5.7 cm. Thickness of the blade 1.33 cm. The last one, number of blades will be 12. That is what I can talk about the 3 different types of hydroelectric turbines.
So okay, moving on. Thank you. So next is moving on to the meshing. So actually the meshing stage is one essential step taken to make a prediction of real world behavior with a high level of accuracy. Meaning that meshing help in breaking up the domain into pieces or reduce the degree of freedom from infinite to finite. So a mesh result that approximate a geometric domain is shown in the figure, shown in the slide. As you can see on the left side, showing the first one is Pelton turbine, followed by Francis and also common turbine. As you can see, most of the domain we use solid, and the noded value you can see on the figure, and also number of elements and mesh quantity for all 3 types of turbine is high. So moving on to the next ones.
So thank you Muhammad Ikhwan and Alif Akmal for the previous presentation. So my name is Muhammad Irfan Faiz bin Muhammad Jasni, and my metric number is 198807. So I will continue the presentation by explaining the SolidWorks Fusion CFD, or how to generate the drag force, the lift force, drag coefficient, and lift coefficient. So first of all, from the SolidWorks main page, we choose the assemble, not the part. So after we choose the assemble, we choose the wizard here, the wizard, and we choose the suitable parameter that we want to choose to be exerted to the body of the turbine, for example. So next, choosing the suitable type of fluid, for example gases or liquid, to be exerted to the surface of the machine. For example, for our project, we use water to be exerted to the turbine. So after we choose the water as the medium to exert to the turbine, so we must set our computational domain. Computational domain is basically the region where the fluid that will hit the turbine. As you can see from the next slide, which is there's a computational region which is the rectangle in shape that will exerted to the turbine. And we also need to choose the goals, which is for our report. We choose lift force, drag force, which is in our own direction, and of course lift coefficient and drag coefficient. So for the lift coefficient and drag coefficient, we must input our equation, which is lift force or drag force times by 2 divided by the density of the water times by the velocity of the inlet velocity power of 2 and times by the area that the water will hit the turbine. So after we choosing all of the element that we want, So we click run on the tab above, on the top of the SolidWorks. So this is the result that we will get once we press the run button. So I think that's all for me. So I will pass this presentation to Ahmad Husaidi to explain about the result.
Assalamualaikum warahmatullahi wabarakatuh. Thank you Irfan, Ikwan and Alif for the great presentation before. Hello everyone, my name is Ahmad Husaidi bin Alias and my meeting number is 19856. So today I will continue the presentation with the part of the result. So based on our simulation, we know that common turbine have the highest lift force compared to other turbine design. And we also can see that the drag force of the franchise turbine is the highest, it is more highest compared to other turbine. And if we try to find the net between the lift force and drag force, and we know that common turbine have the highest net force. I will continue more on in the discussion part. So for our discussion, we need to analyze our data. So based on CFD analysis that we obtained from SolidWorks software, common turbine has the largest value of the lift force compared to Pellet turbine and franchise turbine, which is 438.57. This is because the common turbine has the largest contact flat area compared to other turbine, and also common turbine have a wider flat area. They allow the water to push the turbine better than other turbine, and water can flow smoothly through the turbine. Next, if we try to taking the consideration of the drag force from the table 5.0, it shows that franchise turbine has the highest drag force value, which is 79.8399. This may be due to the presence of the bucket in the turbine that makes the water trap in it, which causes the force to spread in many directions as it touches the bucket surface. When this occurs, the resultant force will be lower that eventually reduce the rotational speed of the turbine. All of the design that have their own advantage and disadvantage, but we need to find the best one for being used in the hydroelectric. So when we analyze our data, we know that the best turbine that can be used is the common turbine. This is because common turbine has the highest lift force and lowest drag force and highest net force. That's higher net force of the turbine will causes the turbine to rotate faster and can generate more power. So in conclusion, by using SolidWorks software, we are able to know that different designs have different net force. We are also able to determine the best turbine shape design for hydroelectric, which is common turbine. Common turbine has the higher lift force, lowest drag force, and highest net force. Okay, that's all from us. Thank you, Doctor and everyone.